All right, good morning again. Maybe we can start and perhaps they will join later or just watch the recording. All right, so today we'll continue our discussion about using integrals to get the areas of regions bounded by polar curves. One thing about doing that is we need to have a good idea of how the polar curves look like, because the thing about polar curves, they do not appear exactly, or they do not behave exactly as how they are drawn, because one complication is the value of r, because remember, when you're plotting a point with a negative r value, you don't go into the actual theta direction, but you go into the opposite direction. So that's why we need to be very careful in examining polar curves, right? So let's see some examples. I guess we finished this one last time outside the cardioid. In a circle, let's try perhaps this one. Okay. Let's call it problem 4. Okay, let's set up the integral that will give the area of the region inside r equals 3 plus 2 sine theta, and outside r equals 2. Right? Okay, so again, it would be great to have a nice idea of how the polar curves look like and how it behave with respect to the angle theta. So let's do that here. Let's sketch the graph. Let me just copy this. All right, so first we'll deal with r equals 3 plus 2 sine theta. And if you look at its current form, compare it with the ones given in the table, or the form, compare it with the form that we wrote last time. So it's of the form a plus b sine theta. So this is a limason. And for limason, it is helpful to know what type of limason are you expecting. And the type of limason that we are expecting will depend on the ratio a over b, right? Remember, in our form, this is a plus b cosine theta. So you compute a over b. In this case, it's going to be 3 over 2, and it is between 1 and 2. So here we will have a dimpled limason. All right. And then for limason, when you know what type of limason to expect, it suffices to give or to compute the r values for the quadrantal angles. I'll make a table of r and theta values. I'll use for theta the special angles, in particular the quadrantal angles. So 0, pi over 2, 3 pi over 2. Oh, sorry, I forgot pi. Oops. 3 pi over 2, and then let's do 2 pi. So you plug in theta equals 0 into our equation, so we get 3. Plug in pi over 2, sine of pi over 2 is 1, 3 plus 2, so that's going to be a 5. Sine of pi, plug that in, sine of pi is 0, so we'll get a 3. Plug 3 pi over 2 over to here, we get negative 1 times 2, that's negative 2 plus 3, we get a 1. And at 2 pi, we'll just get the same value as 0, as theta equals 0. All right. Now let's plot these points. I have 3 radial values, 1, 3, and 5. So let me draw some guide circles here. Say this is radius 1. And then say this is a circle of radius 3. Oops. And say this is the circle of radius 5. It's 1, 3, and 5. All right. When theta is 0, we are here. Oops, we are here. And the value of r is 3, positive 3. So my first point would be here. When theta is pi over 2, we'll go here. The r value is 5, so we go in the outer circle or the outermost circle. When theta is pi, we are here. R is 3, so we'll be somewhere here. When theta is 3 pi over 2, will be in this direction, and r value is 1, so our point would be there. And we'll go back here when theta is 2 pi, right? But we are expecting a limaçon with a dimple. And moreover, we have a sine here. Remember, sine is always associated with the y-axis. So that means the graph of this limaçon will be predominantly on a y-axis, right? And since the coefficient of y is positive 2, that means most of the graph will lie on the positive y-axis. So I know that the graph will look like that in the positive y-axis, right? Again, y-axis because it is a sine, and it's positive y-axis because the coefficient is positive. Had it been a -3 cosine, right? Cosine is always associated with the x component. Then negative sine means we are on the negative x-axis. So the graph would have looked like something like this. Majority would be on the negative x-axis, right? Now let's sketch the graph of the dimpled limaçon. We start at theta equals 0. We increase theta. So we'll be here at pi over 2. And then we continue moving. We'll be somewhere here. And then here's the dimple. And there we go. It looks like a convex limaçon. Let me remedy that. It should be something with a dimple. Okay, there we go. Still doesn't look that good. Hold on, let me remedy that a bit. This is one topic I hate because of all the graphing involved. So I should have a dimple, and the dimple will occur here. Okay, I think that's better. Okay. And then r equals 2. Maybe I can get rid of the guide circles here. Delete the guide circles. Okay. And then the next one is r equals 2. That's a circle, radius 2. So that means radius 2. Somewhere here. Oops. Hold on. So it's a circle of radius 2, so it's between 1 and 3. Come on. Okay, there we go. And then let me erase the guide circles. Oops. Okay, let's let's keep that there, right? And then we're looking at the region inside the limaçon, but outside r equals 2. So the shaded region would be this. Inside the limaçon, but outside the circle. Okay. Now, what are the theta values that will be spanned by this region? Well, the first theta value will be here, because the region starts here at their point of intersection, and the other one is here. So we need to integrate from this theta value and until this theta value, alpha and beta, all right? But the good thing is that from the picture, we know exactly what alpha and beta are. Not exactly, but we know their how they relates to the graph of the two limaçons, the two curves. They are basically the points of they are the theta values at the points of intersection. So let's compute for the POIs. Okay. The first is r equals 2. The second curve is 3 plus 2 sine theta. Both left-hand sides are equal to r. So at the point of intersection, the right-hand side should agree with each other. So we have 3 plus 2 sine theta equals 2. Okay, right? Then we solve for theta. So we want the trig function to be isolated on one side of the equation. So we have that. So that means sine theta equals -1/2. And we go back to our unit circle. When is theta equal to, or when is sine theta equal to -1/2? Well, it would be equal to -1/2 at 7 pi over 6 and 11 pi over 6, at least on the first revolution. All right. Now, where are those angles? Well, 7 pi over 6 is this angle over here. That's fine. But 11 pi over 6 is this angle. So if you will integrate from 7 pi over 6 to 11 pi over 6, you will be getting the area of the region between here, right? Because if you try to write an integral from 7 pi over 6 to 11 pi over 6, you start at 7 pi over 6, and then you end here at 11 pi over 6, which is not the exact region that we wanna consider. All right. So we need to measure, or we need to use from here until here, or to use this as our angular span. All right. Now that means we cannot use theta equals 11 pi over 6, right? Because integrating from 11 pi over 6 to 7 pi over 6, you'll start here, but you'll go in the negative direction, all right? So, but we can express theta 11 pi over 6 in terms of a negative angle. We can say it's negative pi over 6 instead of 11 pi over 6. Because where is negative pi over 6? Negative pi over 6 is exactly this angle from here, exactly this angle. But that serves our purpose for the integration, because now I can integrate from negative pi over 6 all the way counterclockwise direction until the second point of intersection. All right. So that's how I knew that I will not use 11 pi over 6, but instead I'll use negative pi over 6. So the area will be given by the mainstay 1/2, the integral from negative pi over 6 to 7 pi over 6. Now, what would be the integrand? Well, if you go back at the region, you imagine this green ray. Imagine this to be traveling like the hand of a clock, but in the counterclockwise direction. So it will start at negative pi over 6. It will travel counterclockwise. And all throughout its journey, you see that the outer radius is always the black curve, and the inner radius is always the red curve, right? So if you continue the experiment, you'll always see that it's the outer is the black and the inner is the red one. All right. So that means we don't have to split the integral up into two pieces, because the inner radius is always the red curve and the outer radius is always the black curve, right? So now here it's outer radius squared. So that's the black curve. We'll have 3 plus 2 sine theta, quantity squared, minus the inner radius, which is always 2 squared, all multiplied by d theta. And that's going to be the integral that will give you the area of the shaded region. All right. Now you can also take advantage of symmetry, because you can notice that this area or this region is of the same area as this region over here. So we can simply perform the integration from negative pi over 6 until pi over 2, and simply multiply our answer by 2, right? Because again, the graph or the region is symmetric with respect to the y-axis. So another acceptable form for the area here is twice times the mainstay 1/2 integral from minus pi over 6 until pi over 2 due to symmetry of the same integrand. So either answer will be fine. So you can choose to integrate all throughout the angular span, or just do half of it and then just put the appropriate factor. All right. Set here. Any questions? Oh, by the way, guys, we finished grading your FRQs yesterday, so it should be up. It should be up in CASA over the weekend. So expect it probably Monday at the earliest. So yeah, I want to say some words, but I don't know if everybody has already taken the exam. So, but there are some common mistakes, and I guess the this test was tougher than the previous ones because I graded 86 papers yesterday in the last item. So I totaled the scores for those 86 papers, and there's only one who got a perfect score, which is uncharacteristic because usually about 5 to 10 students get a perfect score. But you'll have time to look at it. One pointer that you can, when you receive it, one thing to look out for is that remember that the questions are mostly multiple parts or are composed of multiple parts. So you have part A and part B, and you were told to use your answer in part A to do part B. Now, if you get a wrong answer, or if you had a wrong answer in part A, and you use that wrong answer in your solution for part B, but your process is correct, it's just that you have a wrong answer in part A, then you should get the full credits for part B, regardless of your answer, regardless of your wrong answer in part A. So probably that will help. We were told to use that rubric, which I think is fair. So just to make sure, that's one thing you can look at for your FRQs. All right. Okay, so more examples about polar curves. I am actually thinking to defer to spend the entire lecture or the entire lab today talking about examples of areas of polar curves. And defer the discussion of parametric curves on Monday. So I hope that's fine because I think setting up the integral that will give us the area of polar curves is much heavier than parametric curves. So yeah. Let's try one more. Let's try another example. Oh yeah, Brian. I'm not sure if it is posted already, but we just finished grading it last night. So, and again, the thing is that our lead TA is the one who is uploading everything to CASA, so it might take some time for her to upload everyone's FRQ. So expect it to be available probably over the weekend or after the weekend. Okay, let's try another one. This is problem 5. Oh, do you guys have questions? No questions? Have you tried answering some of the quizzes? Everything's good? All right, so for this next problem, we want to find all the POIs of the curves r equals 2 cosine 2 theta and r equals 1, and then find the integral that gives the area, or that will give the area of the region inside the rows but outside the circle. So let's start by finding the POIs. Now for roses, the POIs are obtained by equating the equation of the rows, or equating the right-hand side of the equation of the rows, and plus or minus the value of r, so that we won't miss any of the POIs. Probably, hold on. How will you spot to do that? Okay, perhaps I'll do it this way so that it will come more intuitive, right? So let's sketch the graph first and see what to expect rather than finding the POIs right away. Because again, polar curves behave in a little weird way compared to our Cartesian curves, right? So here, let's try sketching the graph first. So we'll start with r equals 2 cosine 2 theta. This is a rose with n equals 2. So this guy will have 4 petals. Okay. It is usually helpful to find the poles. To find the basis or the tip or the receptacle of the rose. So the base, or what I call the receptacle of the rose, occurs at the pole. That is when r is equal to 0, just to guide us in sketching the graph. So to find the receptacles, so we need to equate, we need to use r equals 0 in our equation. So we get 2 cosine 2 theta equals 0. Solve for theta. So we get cosine 2 theta equals 0. So this is asking us, what are the angles 2 theta whose cosine is 0? Go back to your unit circle and see when is cosine equal to 0. Cosine is equal to 0 at pi over 2 and 3 pi over 2. But since we are dealing with the 2 theta, so we need 2 revolutions around the unit circle. So we'll not stop at this 2 angles, but do another revolution, which is basically adding 2 pi to this guy and to this guy. So this would be 5 pi over 2 and 7 pi over 2. And then we divide both sides by 2 to get pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. So these are the receptacles of your rows. So these are the theta values when the point corresponding to them will be the poles, will be the pole, right? Now, aside from the receptacles, it's also good to know the tips of the rows. The tips of the rows are obtained by solving this equation. You get the trig function. So the trig function involved in our equation is cosine 2 theta, and we equate it to plus or minus 1. Because the tips basically is the longest part of your rows. So we want to know what is the maximum and the minimum value of the trig function. So we have r equals 2 cosine 2 theta. The trig part, which is cosine 2 theta, will be maximized when cosine 2 theta is equal to 1, and it will be minimized when cosine 2 theta is equal to negative 1. And hence, that's why I'm solving this guy. All right. Now, what are the angles 2 theta? Wherein cosine is plus or minus 1. So we'll start at 0. And then it would be negative 1 at pi. It would be positive 1 again, another revolution at 2 pi. And it's going to be negative 1 again, another revolution at 3 pi. Then we solve for theta by dividing both sides by 2. We get the quadrantal angles. All right. Now, if we'll sketch the graph, oops. Okay, let's sketch the graph. Oh, by the way, for this R values, this means let's make a theta, let's make a theta R table here. So here we'll have theta, then R value 0, pi over 2, pi, 3 pi over 2. We knew that this would give us 2, negative 2, 2, negative 2, right? if I plug this in into the equation for R, where is our equation for R? Plug those theta values there, you get 2, minus 2, 2, and minus 2. All right. And then remember, we also have the receptacles at pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. But basically, I only need one radius. So let me draw a guide circle here. Say this is the circle of radius 1. Okay. Now at theta equals 0, r is equal to 2. Theta equals 0, r should be equal to 2. So this should not be 1, so that should be 2. So we have the first point here, right? That's at 0. And then at pi over 4, we know that cosine will be 0, so we will be at the pole. So this would be my first point. This would be my second point, right? And then my third point would be at pi over 2. But at pi over 2, we are supposed to plot here, right? But r is negative 2, so we plot in the opposite direction. So this would be my third point here. Okay. And then after pi over 2, the next angle would be 3 pi over 4. But at 3 pi over 4, we will be at the pole again. We will be at so this would be my fifth point. And then the sixth point would be 7 pi over 4. So this would be the sixth point, which is a receptacle, right? That's 5 pi over 4 there. And then after 5 pi over 4, we'll go at, where are we at? At 3 pi over 2. At 3 pi over 2, supposedly we're here, but since r is negative 2, we plot in the opposite direction. So here would be our 7th point. And then the 8th point would be at 7 pi over 4. And then the 9th point would be again here at would be here again, right? Because it will just coincide with 0 and 2 pi. Okay, now let's sketch the graph. So here's my first point, and then my second point is a receptacle. The third point would be this guy. Fourth point is the pole. Fifth point is this. Sixth point is the pole again. 7 point is this. 8 point is the pole. And then the 9 point will go back there. Okay. So this is your 4 petal or 4 leaf rows, right? And then the other curve is r equals 1, which is just a circle of radius 1. So let's have it here. Circle of radius 1. Let me erase my guide circle there. Okay. And then how many points of intersection do we see? We see 1 here, 2, 3, 4, 5, 6, 7, 8. So we're expecting 8 points of intersection. But if you just equate the two r values, r values together, so remember we have r equals 2 cosine theta, 2 cosine 2 theta, and r equals 1, right? These are two equations. If you put them equal to each other, you get 2 cosine 2 theta, all right, equals 1. What we get is cosine 2 theta equals 1/2. What are the angles 2 theta, whose cosine is 1/2? Cosine is 1/2 at pi over 3. And then 5 pi over 3. And then another revolution, because we have a 2 theta on the left side. So another revolution will bring us at 7 pi over 3 and 11 pi over 3. And then if we divide both sides by 2, we get pi over 6, 5 pi over 6, 7 pi over 6, and 11 pi over 6. So where are these angles? So this is the first angle, pi over 6. Then 5 pi over 6 is here. And then 7 pi over 6 is over here. And then 11 pi over 6 is somewhere here. So essentially, I am missing the other 4 points of intersection. This guy, this guy, this guy, and this guy. I am missing them because at those theta values, r is negative, right? So here, putting the equation of the rows equal to 1 is not enough to get all the points of intersection. So we also need to do is to solve 2 cosine 2 theta equals -1. All right. And this will give us cosine 2 theta equals -1/2. When is cosine equal to -1/2? It would be at 2 pi over 3 and 4 pi over 3. Okay, and then another revolution will bring us to 8 pi over 3 and 10 pi over 3. Okay. And then we divide both sides by 2, so we get pi over 3, 2 pi over 3, and then 4 pi over 3, and 5 pi over 3. So where are these angles? Theta equals pi over 3 is somewhere here. Let's use a different color. There. Finally, we got the 5th point of intersection. Other one is 2 pi over 3. That would be somewhere here. And then the other one would be, the next one would be 4 pi over 3, which is somewhere here. And the last point will be there. So that's how we got the 4 points of intersection. All right. Is that clear, guys? Okay, but just remember we're looking at the points of intersection. So we need to give the points, not just the theta component. So the points of intersection are, the first one would be, the R value is 1, but you have different theta values. So we'll have 1 comma pi over 6, 1 comma 5 pi over 6, 1 comma 7 pi over 6, 1 comma 11 pi over 6. Oh, I made a mistake when I drew the curves there, but anyway, let me show you why. Then the next point is -1 comma pi over 3, right? So we computed it as r equals -1 and then at pi over 3. Well, this is pi over 3, all right? But the radius, I forgot, is -1. So I will not plot here, but I will plot in the opposite direction, which is this guy. So this is the point of intersection corresponding to theta equals pi over 3. And this is what I'm telling you earlier, that polar curves do not behave as how they look, because here you will assume that here your angle is pi over 3, right? But actually here, the point with theta equals pi over 3 occurs here, right? So that's why we need to be careful and do not rely on the graph alone, okay? Then let's just complete the solution. It's -1, 2 pi over 3, -1 comma 4 pi over 3, and -1 comma 5 pi over 3. Okay, so these are the complete 8 points of intersection. But remember, we have another problem here. We need to find the integral that gives the area of the region inside the rows but outside the circle. So inside the rows but outside the circle. So our shaded region will be like this. Oops. Here, inside the rows but outside the circle. Okay, Now, you can integrate on several parts, but I can take advantage of symmetry here. Okay. Now, look at this would be my testing ray. Okay. The green line here. Oops. Let me see. Okay. So this is my testing ray. Remember, I will integrate counterclockwise for theta values, right? So here it appears that I will integrate from 0 until pi over 3. That will give me half of the first petal. And then, but from the third point would be here until this point of intersection here. And then the fifth point will be here until there, and so on. So it would be a little messy if we will integrate all over the region. But I can take advantage of symmetry because I know that each of the petals or the petals are or the petals have the same area, right? So instead of computing or giving an integral for all four parts of the petals, I can just consider one integral and then multiply everything by 4, right? So I can just integrate over here, find its area, multiply it by 4, right? But I can even do I can do even more because here this guy is symmetric to this guy. So they will have the same area. So what I can do is compute the area lying on half of one of the petals and multiply everything by 8, right? And the nice thing about that is that here I will integrate from theta equals 0 until the first point of intersection. And what was the first point of intersection? The first point of intersection occurred at pi over 6, right? So basically, this is just an integral from 0 to pi over 6, right? And see what part of the region was covered by my green ray here. It only covered the area lying on half of a petal, but there will be there would be 8 of them, right? So taking advantage of symmetry will tell us that the area will be 8 times the area of one of those regions. This would be from 0 until the first point of intersection, which is pi over 6. And then it's outer radius squared minus inner radius squared. So again, let's go back to our testing ray here. As the ray travels from 0 until pi over 6 in the counterclockwise direction, you always see that the outer radius occurs at the black curve, and the inner radius always occur at the red curve, right? So no need to further split the integral up. So here the outer radius will just be the rows. So we'll have 2 cosine 2 theta quantity squared minus the inner radius, which is your equation for the circle, all multiplied by d theta, and then ending brackets. All right. You could have also selected to integrate, say, over this angular span from here until here, but you need to make sure you have the right theta value, right? Okay, any questions? No questions? Is this clear? All right, let's try one more. Yeah, we still have 9 minutes. Unless you have questions, just let me know. Let's do problem 6. So we'll have the region inside both r equals 3 minus 3 cosine theta and r equals 3 minus 3 sine theta. All right. So here are two polar curves are both limacons. All right. One is dominantly on the y-axis, in particular in the negative y-axis. The other one is predominantly on the x-axis, in particular in the negative x-axis. But in either case, both are cardioids, right? Both are cardioids because if you look at A over B, both are equal to 1, right? So both are cardioids. So let's let's compute the values at the quadrantal angles. So let's start with r equals 3 minus 3 cosine theta. Look at the value of r at the quadrantal angles. Okay. Plug these theta values into the equation for r. 0 plug in here will give us 1. So here we'll get a 0. At pi over 2, we get a 0. So we get a 3. At pi, we get -1. So we get a 6. 3 pi over 2, we get a 0. So we'll get a 3. And then it will just be a 0 again at 2 pi. Okay. Now let's sketch the graph. Okay. Now, what are the radius? What are the radii here? 3 and 6. So let me draw a guide circle here. Say this is the circle of radius 3. And say this is the circle of radius 6. Okay, yeah, radius 6. All right, and then let's plot the points. At theta equals 0, we are here. The r value is 0, so we will be at the pole. That's our first point. Second point, theta equals pi over 2 here. R is equal to 3, so we will go to the inner circle. Third point, pi is equal to theta is pi, so we are here. R is 6, so we'll go in the outer circle. And then 3 pi over 2 will be here. Radial value is 3, so we go here. And we'll be back at 0 when theta is 2 pi. So if you'll draw the curve, you'll start here. And then we'll get this guy, right? So it's a cardioid, a heart-shaped graph, but it should be rounded. Limosons are rounded graphs, so yeah. And how we trace it, we start here, going there, completing the heart-shaped graph. All right. And this is what we expected. We said this has a cosine, so it will either be on the positive or the negative x-axis. And since the coefficient of cosine is negative, so that's why we are on the negative x-axis predominantly, right? Then let's do the other thing, the other curve. So let's sketch r equals 3 minus 3 sine theta. Let's compute the r values for the quadrantal angles as well. Okay. When theta is 0, we get a 3. When theta is pi over 2, we get a 1. So 3 minus 3, that's going to be a 0. At theta equals pi, we get a 0, so we get 3 here. Sine of 3 pi over 2 is -1, so I'll get a 6 here. And then I'll get a 3 here. All right. Oh, is this correct? Sine is 0. So I get, because it doesn't seem symmetric. Did I do a mistake here? 0, so that's going to be 3. Pi over 2, this is 1, so that's 0, good. At pi, this is 0, so get a 3. At 3 pi over 2, this is -1, so I'll have a 6. And at 2 pi, I'll get a 3. Okay, let's sketch the graph. First point, theta equals 0, r is equal to 3. So we're here. When theta is pi over 2, we'll travel here. We'll get 0 units. So that means we are at the pole. Third point, at pi, r is equal to 3. So we get this. At 3 pi over 2, r is equal to 6. So we get this point. And we'll be back at 3. Let me just, okay. Then let's sketch the heart-shaped graph. So we start here. We go here. Okay, there we go. It should be more rounded. Hold on. I'm actually just drawing a heart, but it should be more rounded. Okay, something like this. Okay, then let me erase the guide circles. Okay, and then we want to get the area of the region inside both cardioids, right? So where is that region? They should be inside both cardioids, so that would be here. All right. So that would be our the shaded region that we're interested in. Let me see if that's correct. Yeah, they should be both inside. Oh, this should also be included because that little area here, this guy, is still inside both cardioids. This guy is still inside both cardioids, but this guy is outside. All right. And then let's see. What are the theta values? Well, we start here at theta equals 0. Okay, so this is my testing ray. The actual first point will occur from here until there. Oops, until there, right? So that would be my first area. So I'll look at when is, I'll start at theta equals 0. Okay, but in that instance, if I travel, if I radiate this green ray, I see that from here until the point of intersection, I only have one radius, right? Maybe let's zoom in a little bit here. Oops, make this shorter. And then let's zoom in. Okay, right. So here's my testing region. So from here until there's no region, but it becomes clearer when you're somewhere here. We only have one radius. So that radius started from the pole. Oops, yeah. It started at the pole and will end at the black curve, right? And then after the point of intersection, we only have one radius again, but that radius will be corresponding to the red curve. All right. So what I'll do here is, actually I can also use symmetry and say that, oh, this guy this region is symmetric to this region. So I just need to integrate from here until there and multiply my answer by 2. So I'll need to see starting at starting at theta equals 0 until the point of intersection. All right. And for that, I will integrate the black curve and then multiply the answer by 2 because this guy has the same area as this one. All right. So now my area would be at that point of intersection. Now, what's the first point of intersection? Well, it's important, so let's solve for it. The first POI. Actually, I'm running out of time. Perhaps let's continue it next time. Probably can try or start trying to find the points of intersection. For this ones, r equals 3 minus 3 sine theta. So here you'll see that we'll have the equation 3 minus 3 cosine theta equals 3 minus 3 sine theta. So solve for theta. And then let's continue the solution on Monday. All right, guys, any quick questions before we call it a day? None? Okay, guys, have a good weekend and let's see each other again on Monday. Bye.